Hey, what's going on, guys? Komikigins here. In this video we're going to learn how a test program for Apple I computer worked back in 1976. So a few words about the Apple I. It's the very first computer by Apple. So the Apple Computer I, originally released as the Apple Computer and known later as the Apple I or Apple I, like the Apple-1, is a desktop computer released by Apple Computer Company, now Apple Incorporated, in 1976. It was designed by Steve Wozniak. So this is the image of the computer. It didn't have neither the keyboard nor the monitor as the part of the computer itself. So it was just a bare board, right? So the user had to take a keyboard from somewhere and also find a monitor, plug all the stuff together, and the user manual I have here was actually explaining how exactly this can be done. And if you're interested about the hardware part, I highly recommend to watch How Apple I Computer Works by 8-Bit Guy. That's the video I've been inspired by as well. And on the contrary, I want to focus on the software part. So let's imagine that you've plugged everything in and everything works, computer boots. So what you should see if you boot the computer is just this blinking screen. So now we're coming to this part in the user manual where it's time to input the very first program. So what we're going to be doing in this video, we'll input this machine codes, and then I will disassemble this machine codes to have a look at how the 6502 assembly, how the corresponding 6502 assembly mnemonics look like, just to figure out how this worked. And then we'll try to figure out how the characters were displayed on a screen, so how exactly that was implemented. All right, so without further ado, let's actually start. So after attaching the keyboard, display, and AC power sources, you can try a simple program to test if your system and the attachments are functioning together properly. While it doesn't test many possible errors of the microprocessor system, the test program will test for correct attachments of the keyboard, display, and power supply. So just the bare minimum test. And let's actually start. So hit the reset button to enter the system monitor and reset. And we are in the system monitor. And by the way, the system monitor in Apple I was in the RAM of only 256 bytes. And this was a sort of a hex editor where you could just enter the raw machine codes and then either list the machine codes, or to execute this. Well, at very least, that's the only thing that I've learned about this computer so far. So anyway, so a backslash should be displayed, which it is, and the cursor should drop to the next line, which it does. Okay, and now here is the program. So currently, without trying to figure out what this bytes mean, we just try to type them in and make sure it works, and then we'll have a look at the disassembling. All right, so I just want to make this always on top. Give me my camera back, and now here, so 0, I believe this stands for address, so A9 space 0 space AA space 20 space EFFF space E8. I'm just typing those guys here, these bytes, E8 8A, okay, 4C 2 and 0. Okay, and hit return, or I can hit enter on my keyboard, and now type this, so 0.A, and this should list the program, which it does. And if I did input all the bytes properly, then if I just now type R and hit enter, it should, in theory, the program should then print out on the display a continuous stream of ASCII characters. To stop the program and return to the system monitor, hit the reset button. To run again, type R. Okay, so I just type R, and yeah, it seems like it's working. So it's printing all the ASCII characters we have continuously, which it does, and I believe if I hit reset, it just drops back to the shell, right? and which it does. And let's try R again, and it still does the same thing. So the program is still in the memory, so I can run it. So even if I reset the computer, it's still, well, probably not reset the computer. Well, I'm not really sure what this reset button actually did on Apple One. But anyway, so we still have the program being in the memory. All right, guys. So this was cool, right? So this works, but we have no idea how exactly this works. And a little spoiler ahead. So I already know that these are obviously the machine codes for 6502 processor, which is Apple One is based on. So let's try to type these bytes into a disassembler, and then see the 6502 assembly language mnemonics to have a better idea of how this works. So here I have a tool which I've taken from Easy 6502 ebook by Nick Morgan, who has adopted this 6502 simulator. Yeah, so what we can do here, so if I just say declare byte and just would have been putting the raw bytes here. So starting from, so $sign stands for hexadecimal, so starting from A9, and then the comma separated values, so then 0, 0, 0, then AA, and then 20, right, 20, then EF, then FF, then E8, E8, then 8A, all right, for C, and, well, I guess 02, right, 02, and 00, right, and 00. So if I assemble, I hope this, yeah, it does assembles 11 bytes, which is great. And now let's have a look at the disassembling. So we just can copy this and bring it back here, and here is our program. Okay, yeah, now it gets clear what it does, really. So the very first thing to do, we reset the A register, so A is going to be equal to 0. Then we transfer the value of A to the X register, TAX, okay. Then we're calling jump to subroutine, so calling subroutine at this address. And this is the most interesting part with this video, by the way. So this is how the echoing of ASCII characters to the display is happening, which is what I'm currently interested in, because I'm building a 6502 simulator, the bootable one, and I really want to mimic the way how the input and output, how the I/O worked on Apple One for potential compatibility with Apple One software. I'm not looking for 100% compatibility, but anyway, I'm really tempted to know how this input and output worked on Apple One back in the day. So that's a bit of a word on my motivation. Why am I doing this, right? So then we want to increment the X register by 1, and then we transfer it back to A. So literally what we do here, so we want to have, so in the A register we want to have one value greater every time, right? So let's say here, well, I already know, a little spoiler that, well, I already know that this stands for echo. So I'll demonstrate you this. So this echo character, right? And if I put a label here, echo, and let's not do anything here because this system is very different, doesn't even support the ASCII characters. It just allows to print like pixels to this tiny little display. So here we just want to return from subroutine. Did I actually, is this the right command? I'm sorry guys, just hold on a sec. Yeah. Is this really a return RTS? Is this the case? Yeah, RTS, return from subroutine. Yeah, this is correct. Okay, so here we just return All right, and then we jump to, well, actually, it jumps here. So also here we want to, let's put a label called, for instance, next. And here we can just jump to the next. Now we assemble again. Okay. Oh, sorry. It's just the label, assemble. And now see what happens within the debugger, right? So the first step, we reset the value of A register, so nothing special really. Then we transfer it to X. Nothing happens because at the A register we have the value of 0. Then we kind of like outputting this character to screen, so nothing happens, but let's assume that this has just happened. And then we increment X by 1. Well, actually we didn't yet go there. Yeah, here we increment X by 1, and then we put the value of X back to the A register. So the next step, A would be equal 1. All right. And so now A is equal to 1, okay? And again, like we transfer it back to X register, then we call this print echo, and now it's gonna be printing the next ASCII character. So not the 0 character, but the character 1, like ASCII code 1, etc. Okay, and then it increments X again, transfers it back to A, and here, and this is the way how we can like increment the A register many times until it reaches the value of FF, I believe, right? And then it just wraps around and becomes 0. So if we just run this, you see like the A register wraps around, and yeah, and this negative bit is blinking. That's because when it gets to, when this the most significant bit gets set, it just the negative flag gets affected. So it's pretty natural, right? So we just loop around over the values from 0 to FF in the A register. Since we don't have the increment X, increment A register instruction, we just transfer it to X, we increment X, and then transfer back. And every time the value of A register has been incremented, we want to echo the character. And now the most interesting thing here is actually, well, let me just cut this. Update paste. I just don't really want to be torturing it anymore, right? So now let's have a look how this how actually this echo works. So that was the address FFEF in big endian or EFFF in little endian byte order. So if we just now go to, well, here by the way this is the source code of the hex editor. Well, I call it hex editor, they call it monitor. So this this interface that we have loaded into. So here is the source code for this interface to allow us to input the bytes, to list the program, to run the program, etc. And the interesting thing happens here. So if we just, well, let me just actually not making this always on top, because yeah, it's still like, hold on a sec. I'm just wondering, yeah, so yeah, here it is. So here is the address FFEF of, this is the address of where our program has been jumping to. Well, actually, not, well, it's not really jumping, like calling the function call. So it called the function echo, and here is the label. So we have, so these lines is the function to echo the character. Now let's have a look how this echo command works, because it's the most interesting, the most essential thing to consider. So yeah, it starts from, hold on a second, it starts from here, right? From here. So it tests the bit at display. It already has the commentaries, but here it doesn't yet get that clear what exactly is happening. So it checks for so they call it the 7th bit. So they check for a 7th bit if it's cleared or if it is set. So if it's not set, then we branch in on minus in this case. So we just wait until it gets set. Once this bit has been set, we can actually write the value to the specific memory address, and this would result a character being echoed to the screen. But just to have a little bit better understanding of what's going on under the hood, I just want to show you this sort of a thing. So as far as I could figure out what the PIA stands for, so it most likely stands for peripheral interface adapter, well, I believe. And well, anyway, here we have the keyboard. There is what this CR stands for is like clear register, or hold on a sec, just we'll now see what this stands for. Control register, control register, yeah. So CR stands for control register. So here are the most essential variables. So we have the display, and this is the address. And you know that we don't have the very last bit set here, and here we have this last bit set. It's not clear from the hexadecimal perspective, but if I just now type this in binary, you will now understand what am I talking about. So keyboard input, so address where to read the keyboard input, I believe, and the control register, but we don't care about this for now. What we care about is the display. So this is the address of where actually the variable gets written to. I'm just wondering, hold on a sec. Yeah, here it is. So it gets, so STA to DSP, so to display, so it's whatever value we have in the A register. So you remember that the value in the A register has been increased every next iteration of the loop, and whatever value we have in the A register we then set to this address D012, right? And now in regards to this last bit here, so here is what they say about it. So output to display. So yeah, this is a bit of a duplication. Lower 7 bits are data output. Higher bit is display ready. Display ready input. So 1 equals for ready and 0 equals for busy. And here down below they have this nice little schema. Where is that? Where is that? Hold on a sec, guys. Just I lost where that was. Oh, here it is. Is it? Or nope. Yeah, I'm sorry. Just hold on a little bit. It was here somewhere. Yeah, I'm sorry guys, yeah, here it is. So here I found the schema representing the input and keyboard and display interface. So here we have this bits from like 7 bits to hold the value of the ASCII character, and this, the bit 7, what they call bit 7. So if it is equal to 1, this means that display is ready to output the character, otherwise we need to wait for that. So, and that's the reason why they have this loop, so it jumps back to echoing, so on minus. So if it is equal, so on minus, this means that this bit is set, right? So hold on a sec, I just want to double check this. Lower 1 equals ready and 0 equals busy. Well, then it's a little bit strange on why branch on minus, it should be actually branch on plus. It should be branch on plus, not branch on minus. And actually this is stated here, branch on plus. Well, I'm not sure. I don't believe there can be an error in the manual, to be honest. But actually what they state here, so if 1 is ready, so if it's oh yeah, so branch on, that's okay guys, I feel a little bit lost about this, so I'm not sure, okay, let's have a look at branch minus. Just want to make sure how this branch minus work. Yeah, so if you think that there is an error in the manual, probably there is an error in your head, so you really need to double check your own self. So BMI, branch on minus, Control F, BMI, yeah. Branch on minus. So it doesn't mean that we branch when this negative flag is set. I'm not sure really. But anyway, well, okay guys, I'm sorry, I'm not ready at the moment to say exactly how this did work, but what I can say for sure is that this code, so this branch on minus waits until the 7th bit at the address of display. This bit is being equal to, I believe, 1, and if it is, then it sets the character to display. Otherwise, it just jumps back to the echo and waits until the display is ready. So this is a bit of a hardware stuff. And now I just want to demonstrate you this in the binary format. So D0, 1, 2, okay, and here D0, 1, 3. So here we have D0, 1, and here either 2 or 3. So yeah, it's pretty simple. So it looks for this bit. So if this bit is set, right? So according to the code, it's very less. So if the bit is set, I'm not sure if branch minus actually branches if this bit is set, then probably the negative flag would get affected, which definitely should be the case. But in this case, it would be set in the character if it is 0. And in the documentation, they state the opposite. So 1 equals to ready and 0 equals to busy. Yeah, so it's a little bit unclear, but anyway, the idea again, like the idea is just to set the bit only in case if it's ready, if the display is ready. In this case, we write whatever we have at the A register to this address, to DSP, which stands for display, right? So we write to this address whatever we have in the A register. That's pretty much all about it. And that's how the character then gets printed, echoed to the screen. And another thing I've been reading about Apple One previously is that the teletype, so-called teletype mode, it means like you just type the character in, it just gets printed next position, and when it gets to the very end of the screen, it just goes to the next line. So this kind of teletype output is hardware implemented. So that there is a hardware implementation with it. I have no idea how that works, but that's well, I guess yeah, probably 8-bit guy told about this in his video on how Apple One works. Probably I took this from there. I don't remember at the moment, but probably that was the case, right? So yeah, but anyway, I don't know how about you guys, but for me personally, disassembling this tiny little test program for Apple One and figuring out that the matter of actually typing the character to screen on Apple One was just the matter of single STA instruction to the certain address is really awesome. And that is something that I'd like to mimic in my bootable 6502 processor simulator. So potentially to have a bit of a compatibility with this Apple One software that was built back in the day. Well, ultimately, I want to try to actually be able to run this entire monitor program, which is 256 bits. I have no idea if I would ever be capable of doing that. It's really lots of work is needed, and I currently have just two addressing modes for LDA instruction, like the immediate and the zero page addressing mode, and tons of work to do. And I don't know, probably I would refactor the code 1,000 times more. So I have no idea whether I complete that project one day or not. But anyway, this is a really simple and straightforward kind of like design solution to output the characters by simply setting the value to a specific memory address. So set the value of the ASCII character to the specific memory address to get it printed to screen. And for my simulator, as far as it's not an emulator, I don't really need to implement this display waiting to be ready to output, and I don't also have the processor cycles being taken into account. So it's just it's not an emulator, it's just a simulator. What am I building? So I think it would be just fine and just okay to just write the well, I can still just for compatibility purposes, I can still use this branching, but actually the bit at DSP, the bit 7 would always be set, because in my case the display would always be ready, and that's how I'm going to achieve this, a bit of a compatibility with this Apple One computer, how it was implemented, so that the software for that potentially would be working as well. It would be light and fast as opposed to how it was back in the day, because again, like, I'm not taking cycles into account. But anyway, at least to have some programs to work, at least having some programs working, and having like some code from back in the day running it on my simulator would be really awesome. And I believe, yeah, this is gonna be cool if I ever manage to do this. Okay guys, so this is it from my side. Hope you've enjoyed the video, and well, I'm sorry I don't know everything about this, but again, like, this was a very long time ago, and the only source of documentation I've found so far is this Apple One manual from 1976. So it's more like about guessing rather than knowing for sure. But anyway, some of the most essential things I'm interested in were actually revealed. So I think I'm happy. I'm quite pretty happy with this result so far. So I hope you are happy with this as well. So yeah, this is it from my side, guys. Thanks for watching. Until the next time, and take care.